Good evening. Welcome all. This year, again, we're together for the İhsan Doğramacı Memorial Lecture 2024. We are honored, very happy to host one of us here today. The program is going to be of four main parts: the opening remarks, followed by movie screening, and then we're going to go into art. We're going to hear Gustav Mahler's piano quartet movement in A minor. Adelia Ateşoğlu is the teacher, and İdil Dündar in violin, Melis Güney in viola, Ayça Çit in cello, İlkay Günaydın in piano is going to perform. Having said art, I also want to bring your attention to the art piece over there. Actually, this is not an image that was taken from the internet. This is original. It is a human AI interaction. So, where is Barış? Okay, please stand up. Barış, our PhD program student, a graduate of Hacettepe Medical School with flying colors, did this work. We will then continue with an introduction to Mete Atatüre, followed by his conference. Now, I would like to invite our rector, Professor Kürşat Aydoğan, to give his remarks.
Dear colleagues, distinguished guests, thank you for attending the İhsan Doğramacı Memorial Lecture 2024. This is an event organized to once again commemorate Hoca Bey, his exceptional contributions to higher education, health, and sciences. This year marks the 40th anniversary of Bilkent's establishment. So it was in 1984 that Bilkent University was established by the decision of the foundations. So we are putting all the effort to advance as a globally recognized research university. And along this path, we take pride not only in the scientific achievements of our faculty members, but also the accomplishments of our alumni who are making waves in the scientific community. This year, we have invited one of our esteemed alumni, Professor Mete Atatüre. He's a graduate of the physics department of Bilkent in 1996, and currently he's the head of the Cavendish Laboratory at Cambridge University. He kindly accepted our invitation and honored us with his presence at this event. This event holds a great sentimental value for us. So I'm confident that his speech will inspire both us who are here and also the young students and researchers who are watching the conference live on Bilkent's YouTube channel. Before I hand the stage over to our Dean, Professor Tayfun Özçelik, later to introduce Mete Atatüre and his speech in detail, I would like to briefly talk about the importance of the building just we are in. This, as you know, İhsan and Ayser Doğramacı Science, Culture and Arts Center was opened for use by Bilkent community last year in 2023. This building, which Hoca Bey and his family donated to İhsan Doğramacı Foundation back in 1991 and served as the residence of Doğramacı family until 2018, now hosts scientific, cultural, artistic, and social events in line with the foundation's mission. Once again, thank you very much for participating in this meaningful event at this center, which represents a sentimental value for all of us by preserving the memories of Hoca Bey and Ayser Hanım. Thank you.
Thank you very much. Okay, before I start introducing our guest, let me say that it takes a village to put these events together. And we are all grateful to the people who organized this event. In introducing Mete, I would like to start with mentors. And I'll try to link two school of thoughts, lessons of wisdom by two father and son schools. After all, I'm a geneticist, so father and son. But to make it into context, I would like to first take you down the memory lane. Geçmiş zaman olur ki hayali cihan değer. This is, I think, 2006, when Aziz Hoca was with us for the opening of the Jim Watson exhibit here in this location. Over the years, actually, we had excellent speakers for this event. It's now 25 years. And again, let me begin with Aziz Hoca, who discovered DNA repair, got his first doctorate degree in Turkey, from Bilkent University. Harold Warmus, who is a Nobel laureate, a Lasker awardee, president of the National Institutes of Health and the president of the Memorial Sloan Kettering Center, who discovered oncogenes, was with us. I remember very well with Abdullah Hoca, the evening we had together. Of course, our pride, Gökhan Hotamışlıgil, and also Peter Walter, who pioneered the endoplasmic reticulum stress, which is at the center of metabolic disorders, was again here with us. Jeffrey Friedman, I don't know if anyone is taking these medications now to lose weight. Glucagon-like peptide 1 inhibitors. Actually, it is the blockbuster now in the entire world. There was recently a documentary in CNN, Sanjay Gupta covered the subject. Actually, this all started with the discovery of Prader-Willi syndrome in 1992 and followed by leptin hormone. And he was with us in 2013. Bruce Alberts, president of the National Academy of Sciences, was with us in the coming years. I think you see one of our faculty members. He's the author of Molecular Biology of the Cell book. This is one of the major books that Turkish Academy of Sciences also translated into Turkish. And here, Işık Hoca is asking him to sign the book. And most recently, we hosted the president of the Nobel Committee last year here. Okay, these two schools of thought. Here is Arthur Kornberg, who discovered the Nobel Prize who received the Nobel Prize in 1959 for the first biological synthesis of nucleic acids and ribonucleic acid and deoxyribonucleic acid. Following that, his son, in 2006, studied the molecular basis of eukaryotic transcription, which is a continuation of his father's work. They are both professors at Stanford University, and I took the biochemistry course from this father-son pair. This is actually in the course. I think nobody heard this before. I'm now sharing it with you. Arthur Kornberg, we were a small group of students, and he started the lectures by introducing us to the 20th century in life sciences. And he divides it into periods. Microbe hunters in the 1900s to 1920s. Then comes the vitamin hunters. This is not an easy subject because remember, in the previous 2-3 centuries, all these expeditions in the oceans and people are sailing for prolonged amounts of time without eating fresh produce. And then they start developing diseases, serious diseases. So vitamin hunters, actually, if you go to Budapest, the famous opera house, and you go back a few streets, there is a famous high school there who graduated several Nobel laureates. And the Hungarians are the ones who were really instrumental in the vitamin hunting business. Then comes the enzyme hunters in the 1960s, gene hunters in 1980s, and he wrote the book actually in 1980s, and this is his book, and the same thing is in his book. He looked at the future and anticipating that neurosciences is going to be a field for the future, he called them the head hunters. Now, in one of his first lectures, Professor Kornberg, who was contemporary of our father and worked at the same institution in St. Louis, showed us a picture. Not this picture, I got this from the internet, but in that picture, he described to us when he was a medical student, he was sitting next to the patients and through the night counting the drips of the IV solution that's going into the body and also counting the other end so that the balance of fluid is so critical for the patient. This is a lifeline. I mean, this is how the patient lives. Then he shared with us a paper that was important in his medical studies to advance from counting the drops to investigative approach. And this is a New England Journal of Medicine paper published in 1946, August 8, with one author and our founder. It is about scurvy for the vitamin hunters, if you remember, please. This is the major disease, vitamin C deficiency. And he makes a survey of these patients, one of the best papers of its time that was instrumental in his studies, the investigative approach. He knew I was from Turkey, and he called me and also told me this story. Of course, this is my fall 1980 89 semester lesson that I learned. Lifeline of knowledge is research. Have a deep understanding of the history of the field. So my mentor was Arthur Kornberg, and the proof of what I learned was the scurvy paper written by our founder. Now, the second part. You know, these events that we organize together in this environment, actually, in the 2000s, one day, we have again a prominent speaker, this time the legendary Mary Claire King, who discovered the BRCA1 gene in breast cancer. And Hoca Bey summoned me. He said, come here 10 minutes early. And I came here with Ijlal, and over there was the couch. And come here, come here. So we went there. And there was one more individual with us, a senior. And he asked me, tell me, I have to go into Turkish here. Bana harifi anlat dedi. Şimdi ben durdum. O yanımızdaki kişi de dedi ki, hocam dedi, gelen dedi misafirimiz bir bayan. Şimdi hoca bir tebessüm etti. Harif dedi, işinin erbabı, ne yaptığını bilen sofra arkadaşıdır. Arapça bir kelimedir. Ben hiç konuşmuyorum. Döndü bana. Sen dedi, hiç konuşmadın. Arapça mı biliyorsun dedi. Hocam dedim, bilmiyorum dedim. O zaman dedi, neden sesini çıkarmadın dedi. Ah dedim, hocam ben Arif anladım dedim. Baktı, güldü. Ama dedi, ben dedi, kız tarafıyım dedi. Kızlar dedi, nazlı olurlar dedi. İclal'e iyi bak dedi. O akşam da yanına İclal oturdu. Ben anladım ki o ders, bu ilk parçası, kalpten kalbe bir yol var. Özellikle, if you think science is a social enterprise. And I learned it from our founder. And the proof is, of course, our university. Later in the years, I learned more. And let me share with you. One day, I was invited to Brno in Czech Republic to Mendel Abbey. This is where Mendel worked with his piece, to give a talk about the interaction between science and art. And after the talk, actually, Elizabeth Watson became a very good friend with Ijlal and brought Jim Watson, and we spoke. A few weeks later, I received a letter. Watson is inviting both of us to his home in Cold Spring Harbor. Of course, we were thrilled. We went. We stayed in the house. Gece yatıya kaldık. So we had pajama talks. And there, I learned something incredible. You see here the picture he took us and showed us that this is the first house he lived in. You know, from his books, he's a prolific writer, and says, I had two interests at that time, either to get a girlfriend or do research. I couldn't get a girlfriend, so I had to do research. In Mete's institution, he discovered DNA. In 1968, I think 5 years or 6 years after his Nobel Prize, he got married to Elizabeth Watson. But the interesting thing, now comes the important part. His father happened to be ill. And in the house, they did not have an extra room, so his father was sleeping in their bedroom, the newlywed couple. And they had to sleep in the veranda of the house. Then, at the end of the summer, the father passed away. And this was the honeymoon time. You know where they came and who hosted them? They came to Ankara, and our founder hosted them. Yeah. So, again, so many years later, this kalpten kalbe yol vardır worked. Let me give you a very recent example. Last night, Aziz Hoca called me to congratulate about something. And we spoke. And then he said on the phone, Mete'nin gözlerinden öpüyorum. Then he wrote on top of that. And Prensesle Paşa'yı da benden okşa. Prensesle Paşa da oradalar. Now comes the last one. In the spring semester of 2000. Again, we had an İhsan Doğramacı lecture speaker. And Ali Doğramacı Hoca, told me, elephants like the company of elephants, he said. Yes, he was right. Sometimes begins with finding a baby elephant, continues nurturing with conceptual rather than factual information. Of course, factual information is also very important. And then, let it happen. I mean, of course, you are the most discerning taste, but your default setting is not on no, it should be on yes. And the audience here, hocalarım, are actually the ones who found this little baby elephant. I see Atilla Hoca here, I see Şefik Hoca, I see Cemal Hoca. So these all proved that it is true. Actually, today, Mete, just before coming here, these pictures were taken 1 hour ago. The baby elephants, these are the baby elephants of 2024, talking to him. So, I think Mete doesn't need an introduction. He is the chair, that is Newton's institution. He holds the chair. So I invite our elephant to make his presentation.
It's been a day of emotions. Coming back to Bilkent is it won't be just another trip. So when I say it's sincere honor to be here, it's not the usual thing you say, and I'm not saying it for the sake of it. I do mean it. I'm emotional even now. So excuse the voice. But I did grow up here. Many people who contributed. I very much like the elephant analogy. Many people in this room have contributed to bring me up, keeping me on course, even when I was derailing. They know me as the little rebel boy who hangs around in the Fen Fakültesi with scruffy clothes. There's no tie, and that's on purpose. It's at all not about respect or disrespect. It's just to tell them that I'm still that scruffy boy, and I'm still out to learn physics. So hopefully that comes across, despite the white hair. But the hair is still long, so that's I keep that going. And it's I agree with everything that was said about the university. It's one of those universities that. There are many in Turkey, but it's one of those that really started with a vision, with a very, very grand vision. And it was a go big or go bust approach rather than let's play it safe, let's start small. It really had a vision, and the vision went anywhere from the very top, obviously, to all the way to the research assistant that saw me when I visited as a high school student and said, can you tell me a bit about the physics department? And the research assistant then, PhD student at the time, said, sure, I'll take you around. And he actually spent half a day going through labs and having discussions. And that was the thing. That made me decide to come to Bilkent, or study hard so I can make it to Bilkent. We didn't have open days back then. It was more just a university exam. Alkan Kabakçıoğlu was the research assistant at the time. And I was lucky that I bumped into him. Right? And it shows you that across all levels, across all positions in their careers, the place was it had the vibe when I started, and I was very happy to be part of it. So, and that's why I hope you're convinced that I'm really emotional at the moment. So, so I like to get on with the part that's less emotional, so we can get my voice back. So the title is A Quantum Tale of Gemstone and Light. It's, of course, a play with words. It is a bit of a tale. The gemstone part will come clear when I talk about how quantum optics and material science combine, and the unexpected material that actually has been playing some critical roles, important roles, pushing the application side of quantum physics forward. And I will reveal what it is. It's diamond, and hopefully I'll convince you that it's an interesting system to play with as a physicist. Any data that I show, any measurement, any results that come out from our lab, among others, I will be showing, but anything that comes out of our lab is from the group. So I wanted to start just by thanking my new elephants, baby elephants, that I'm very happy to work with, and people have had they've come from all around the world, including Turkey, and I'm very lucky to work with them. It's a fun group. It's right in front of our labs in Cavendish. So I'll start with, given that this is an evening talk, so I'll try to do a bit of a challenge. The concept of correlations is key to physics. So obviously my topic is physics, and it is boring if there are no interactions, if there are no correlations. So I have to have interactions, and there should be correlations that yield, that's produced after those interactions. If an object is not interacting with anything, it doesn't really have much physics to study. So we like systems that have interactions, and we like to look for correlations in those systems after those interactions. So typically, if I take two red balls, as a physicist, of course, I'm free to take as simplifications as I like. If I take two red blobs that are not correlated or related to each other at all, and if they're just simply coming close in space and have some sort of an interaction, and as the wiggly lines is our typical way we describe interactions, some sort of an interaction between them such that when they separate again, they scatter from each other, they separate again, some internal property that's not visible here, but some internal property remains correlated. Through the interaction, they have some correlation they hold on to afterwards. That concept means that even when they're far apart from each other, if they can hold this correlation, whatever that might be, we call it the entangled state. We call it the two systems are correlated or entangled, quantum entangled. In the quantum domain, we call it quantum entangled, but that's the concept. Now, this of course, was a very big problem for Einstein together with Podolsky and Rosen. And they wrote a paper with a question as their title, can quantum mechanical description of physical reality be considered complete? It's a very good, of course, fantastic paper. You should, I would encourage any undergraduate in physics to read it. And it simply says, these two things interacted and something happened. But when you separated them, how is it that these two things remain correlated in a quantum mechanical point to which what you choose to do in one of those subsystems, the one red blob, has a consequence over there. They're separated now. They shouldn't have any consequence. And that's why quantum, can it be considered complete? The answer was no. Literally in a few months, a second paper came out from Niels Bohr that said, can quantum mechanical description of physical reality be considered complete? Question mark. So if the answer is the same, this would be a replica, remake of the same results. And you wouldn't really publish that. You would just agree and move on. The answer was, yes, it can be. But it was in a subtle way, more to say there might be more things coming, but the entanglement concept is real. So yes, maybe not every part is polished yet. And let's be honest, it's still not polished yet. But it's not the entanglement, the distant entanglement is not the reason why it's bad. That's firm. That's going to stay firm. In all this discussion, however, they focused on what happens here afterwards. But actually, if you look at that interaction part, the correlation is generated, whether it lasts longer later or not, independent of distance. It's generated because they interacted, and interaction means they were close. Proximity is the name of the game for any kind of correlations to build up. You have to bring two things together so that they interact. Whatever the mechanism is, there will be a characteristic length scale for this interaction. It might be long, it might be short, it might be strong, so it can be done fast. I don't have to keep them together for too long. Whatever the mechanism is, 1 over r dependence, 1 over r cubed, r squared, r to the 6th, there is going to be a relevant length scale where two red blobs have to come close to each other for any effect that you can think of. But there is one mechanism that I know, and I would like to know if there's a counterpart to it, but there's one mechanism where this requirement for proximity is lifted. And that is if they actually have, instead of physical proximity, if they can genuinely exchange energy directly, if I can ensure that energy is transferred in such a way that it goes from one red blob to the other red blob, and through the emission and absorption process, the internal degrees of freedom become correlated, I no longer have to worry about how far apart they are. I just have to make sure that electromagnetic radiation makes it to the other side. That's the only condition. There's one and only one mechanism that I'm aware of through electromagnetism in between, where the two red blobs can be correlated, quantum correlated even, without the requirement to be close by at some point in time. Right? That could be light. If that's simply light, I just have to make sure that there's some line of sight, and then the two red blobs can exchange this. If a photon is absorbed or not absorbed, we can do some tricks with the internal degrees of freedom. There's one more odd thing that quantum mechanics gives us, and that is the concept of quantum erasure. So normally in real life, in conventional lives, if you are measuring something, it's implicit that you want to find out what the answer is. You don't have to say it, right? It's almost, if I want to measure something, it's because I want to know. Quantum erasure is measuring something so you don't know. That's deliberately, you don't want to find out. And neither should the rest of the universe. That's the goal of quantum erasure measurement. You make a measurement in a particular basis, physical basis, in such a way that any information about those two red blobs is erased very carefully, so it's not accessible to anyone. All right? And for this purpose, what could happen is, for example, the two red balls, they might be sending a photon, but instead of between each other or to each other, they send a photon, a light, to a third party. This is where the eye is. And a third party makes a measurement and sees that there's a photon. And the question is, well, where did the photon come from? Did it come from the top red blob or the bottom red blob? If you cannot tell the difference, if you are unable to tell where the photon came, but a photon did come, then you create this ambiguity, and that's what quantum physics likes. And you create, as soon as you do that, you create quantum correlations between those two red blobs. Now, two red blobs, in this final case, they haven't even seen each other. They haven't exchanged any energy. There is no contact between them. But you can create quantum correlations between two objects that they've never been aware of each other until then, using a third party that does the same exchange of information through light. Think of it now instead of two. So first, believe me, this is correct. Right, okay, this might be a bit odd. Was that?
Yeah, right.
Yeah, right, exactly. So believe me, this is correct. Then you can say, is it only two? No. If you are able to do this, you can imagine that you can actually build this. What looks like a network linked. Each ball is linked to another ball or something. Imagine that this is randomly distributed entities where interaction by light in the quantum erasure style that I talked about allows for internal degrees of freedom to be correlated. That I can build up these correlations by pairwise quantum erasure measurements. And imagine, let's say that we have all the resources, we don't need to worry about coherence and all that. Ideal systems, I can weave out interactions between pairs in such a way that I actually, for the same layout of red balls, I can connect the dots in a way that I like, or in any way I like, so that I can start talking about the concept of matter, if you want, where interaction or correlation means interacting nearby, because they're related, between objects that are not actually in the same proximal space. So physical distribution of a lattice that builds up a matter, a piece of material, matter, is freed from where the atoms actually are. Weird, right? Trust me. I'm not going to say it works. It might work. That's where I'll draw the line. So these are different. If you were to build matter by atom, there are different shapes, different lattices that we see in nature, from buckyballs to actual cubic lattices, hexagonal formation, face-centered cubic, whatever the format is. Matter is built mostly by regular lattice formations, other than amorphous stuff. But you can literally build up based on atom by atom placement. What we're capable of today is, instead of an actual matter that happens to be a lattice formation inside, we can actually take these atoms one by one in vacuum and literally by light say, you go here, you go there, you go next to that one, and you can build up different structures, including a cone or torus, Mobius strip, Eiffel Tower. The research was done in Paris. These are individual, all those dots that you see are individual atoms, neutral atoms, that are trapped in space by optical traps in complete vacuum. And you can dial up a lattice formation. But because we can see them, this is actual data, by the way. Because we can see them, that means they're optically separate from each other. So they don't actually interact with each other. They're just there. They happen to just hang in space. The next step, which hasn't been done yet, is to take pairwise entanglement, the quantum erasure experiment, to actually beat topology and have matter that has a certain property that isn't linked to its organization of the atoms. This has never happened. So we have a great opportunity to take the concept of quantum entanglement and correlations at a distance to create synthetic matter that has never happened before, in a way we never imagined before. So what do I mean by that? Very briefly, I'll mention this. I call it I divide it into 4 categories, right? The first category is the obvious one. Real atoms put together and have real interactions with them. That's like real matter, the actual, the wood and everything else, the bismuth. That's what we know as real natural matter that we know today. But there are these 2 other options. Real atoms still real atoms, but put together in a fake lattice, a synthetic lattice, and interactions are turned on and off synthetically by controlling the optical depth of the optical lattice, power of the laser that keeps them all in the same place, all that. That's a different type of material. We call it synthetic matter. And it's real atoms, but they don't actually show me the properties of, say, rubidium as a metal, but it shows me rubidium as a Bose-Einstein condensate, or something completely different, a Mott insulator, for example, simply by tuning different properties of the system. That's a different research now. This is the more active research. Rather than understanding what nature gave us, we're synthesizing nature. But it has limitations. You're limited by the real atoms. The third one is the most exciting, hasn't happened yet, and is also the challenge for quantum technologies. That synthetic atoms, what we call qubits, are actually artificial atoms with multiple energy levels. Can we use those and their interaction as purely 2 qubit gates, which are basically entangling operations to create macro correlations so that you end up with, again, an emergent behavior collectively. I don't care about controllability of every single qubit. I want to know what this whole device does, 1,000 qubits. What is emergent out of it as a property? And that's the direction that one could go with this kind of entanglement system. There's one more which I'm not sure what to say about it. Synthetic atoms with real interactions would be these human-made qubits, effectively physical systems, artificial atoms, but their interaction is real. Probably that means they're too close by and they have some collective modes generated. But I think those three are the most relevant ones. For all of this to happen, we have to control a quantum object. If you don't have control over the red blob, let's put the name to it. It needs to be a quantum object that preserves its quantumness. We have to access it and we have to control it. If you go back to the early letters of Heisenberg and Schrödinger particularly, of course they've done the Gedanken experiment, but it's not because they didn't have the means to do the real experiments. Even in their letters, you see that they ruled out the real experiment, saying, of course one can never isolate a single electron, but if you did, this is how the letters continue. Today, of course, we're far from that. I will highlight 2 Nobel Prizes as 2 big achievements that have led to us being able to control a single quantum object tangibly so that we can work with many of them at the same time. The first one is Demelt and Paul. They've designed a mechanism to trap a single atom in space. That's all those Eiffel Tower that I showed is many, many of those atoms. They're the first ones that actually trapped a single isolated one in vacuum to say that's a single atom. Until then, it was hot gases and large statistical results, but never a single isolated one. And it's basically by creating electromagnetic trap so that the ion is constantly pushed from all directions to a center, and it kind of gets trapped in there. So it's got an electromagnetic field profile. And if you look at Demelt's signature underneath, I put them particularly, you see that after the discovery, he actually changed formally. He changed the signature to include the trap. That's how he trapped an ion. It's amazing. And then the second one is Dave Island and Serge Haroche for the quantum part of that. So they've done many experiments since then, but literally, I would say Dave Island and Serge Haroche actually brought the quantumness into this picture of when you trap an ion, what can you do with it? Whole concept of quantum control, whole concept of building these correlations, entanglements, has spun out of effectively his years of research, their years of research. This is what people call quantum 2.0, the quantum coherence coming in. So here's a photo. I did talk about the trapped ion, so I should at least show it. Here's a photo of a single trapped ion in a trap. This is from Oxford, and you can see a tiny dot in the middle. That's the ion. That's a single quantum object. That's the red blob we started out with. Now imagine having a billion of those, but if one takes all that, that's a bit of a challenge, but let's say a technical challenge. Today, in terms of quantum objects, there are many. Luckily. So we now have capability of doing those kind of experiments, control and manipulation and all that across multiple platforms. The atoms are still there. The superconducting qubit systems are there as well, called atoms as ensembles. Photons themselves, of course, they've played a critical part in pushing forward what quantum physics is. And spins. A single electron or a single nuclear spin in a material itself is also a very isolated, nice quantum object, which allows us some sort of access. So that's also, it works well. And what's interesting is that those two can combine. There are many, now we know that there are many systems that offer the two as a combination. A spin, something that holds spin, is a qubit if you want, but a quantum object. And that spin is linked to optical transition, so it produces single photons. So you can imagine you can create a correlation between the photon and the spin, and then you can send the photon at the speed of light, obviously, to somewhere else. So you can then have correlations that go where you want them to go while you're holding on to one aspect of it in the lab with yourself. So many materials, many physical systems offer that opportunity for us. And today, the field of quantum optics and material science have really been working close together. There's so much work that goes on, combining all the effort of quantum optics, which is more about control, precision, being very accurate, to material science, which is a lot more hand-wavy. It's discoveries, behavior, understanding what material provides, be it dirty or not. So it's a combination of these two different styles of research is what we're doing today. And when these two meet, the quantum optics and material science, for purposes of developing more quantum physics, on the basic science, there's a lot of interesting things going on. This is the hot topic of our era. I would love to talk to you about those guys as well. But there is a lot of physics, and the underlying theme is usually emergence. Complexity, you create many of these things that interact with each other, and it's hard to guess what comes out. And we do these experiments in a way that reveals what their nature is. But there's a second part, and that's applications. The application part is the quantum technologies effort that goes on around the world at the moment. So I'll talk a bit more about the application-driven research that we've been doing. So the three areas, when we say quantum technologies, what are the three areas? Typically, there is quantum computing and simulation. There's one area. Second area is sensors, metrology, understanding what is out there and leveraging quantum properties in doing so. Communications and networks is another area where concepts of security and distributed computing both come in hand in hand. And here is from Optica's, Optical Society of America's website from 2020. I don't think they updated it, but I don't think it needs much update. This is where they expect these three areas to deliver when it comes to quantum technologies. There's atomic clocks, gravity meters, medical imaging for all the sensors. There is a quantum internet at the very end. There's actually something else. If you actually look into it a bit deeper, Einstein isn't convinced because of the photon. Einstein ends up being convinced because of these earlier measurements by Heinrich Weber on diamond. So Heinrich Weber was making measurements on various materials for specific heat at the time. This was a thing to do measurements on. And they all kind of come out same value, no real temperature dependence. Of course, at those times, there's not 1875. There's not much temperature control. You can cool it by, you can cool it down by cold water, ice, but you cannot really do more. We haven't actually, at that time, we don't have liquid helium or something. So it's very limited temperature range. So basically, they showed that specific is more or less identical for all materials except diamond. Diamond has a very strong dependence. And that's something that was not clear why this is the case. And it's only when Einstein looked into that data and realized that the only way he can explain it is by quantizing the vibrational modes, the vibrations of the atoms. So it's the phonon that actually did it. So, and he said, oh, okay, so anything bosonic, I'm going to have to quantize. And then he got convinced and said, okay, well, in that case, I'm okay now with the photon. And that's how it started. So diamond played a key part in the beginning, if you will. So what gives diamond its color? I'll speed up now. What gives diamond its color is not the diamond itself. Diamond is actually lab-grown, especially lab-grown diamond looks like this on the right-hand side. It looks like glass. It's boring. It does not interact with light. The only thing that gives its color is the impurities in diamond. So if you take all the carbon lattice and remove one of the atoms and put another atom, you have a chance of that atom as an impurity interacting with the spectrum, the optical spectrum that we have. So yellow would be more silicon, pink is more nitrogen atoms, blue is boron, so on and so forth. So this is an image from the National History Museum in London. These are different diamond pieces, all heavily doped by an element. Just to show you, we want to build these individual nodes linked together by some optical communication. Individual nodes will consist usually of these three elements. The flying qubits, the photons have to go back and forth. The processor qubit has to be there, the ground state that I talked about, the spin. And there should be some local registers. And diamond conveniently offers us carbon-13 atoms around, the natural isotope, 1% isotope, of having a few carbon-13 atoms around that the electron can talk to through proximity, dipolar coupling. And that becomes the register that we can transfer quantum information. These are the three ingredients. In most systems, this is what's being pursued. So the idea of building the quantum internet, which Jeff Kimball proposed quite some time ago, 2008, basically he put boxes and called it quantum node. You fill it yourself once you find out what it is. And then you put red arrows to say these are the quantum channels. You, again, go and find out how to do that. It's a very nice paper. And the idea is to build it based on these defects in diamond. And Europe is building it based on the Nitrogen Vacancy Center. So the whole Europe Quantum Initiative is building this. And now this is a 3-node system. So correlations by quantum erasure now. The idea is exactly what we talked about. We drive 2 quantum devices, and one of them emits a photon, and not 2, but only 1. If I have this magic element called a beam splitter, so that it's not clear where the photon went, up or down, then and we make a measurement, we cannot tell where the photon came from, and therefore the result is that the 2 are quantum correlated. And when you check that afterwards and you verify this is the case. So it's a very simple experiment, or concept at least. So here's the first measurement that showed this in solid state systems with, again, NV centers in diamond, the nitrogen vacancy center in diamond. And there, this is in Delft, they've separated the 2 units, A and B, across more than 1 kilometer, and they actually demonstrated this entanglement distribution between two systems. Now they operate on 3 nodes, and they're planning on continuing more. And one of the things they've done is actually teleportation. So they've actually teleported quantum information from one area to the other area instantaneously, but of course we know that there's no break of physical laws there. But this was proposed in 1993, and the measurements were done in 2000. So within about 10 to 15 years, they had the first results of this distribution in diamond, using diamond. But that's not, as I said, that's not the only defect that works well. Nitrogen vacancy center is lazy, it's there. You don't have to do anything. In fact, you have to work very hard not to have it, because nitrogen is all around. But there's a whole column called group 4 color centers in diamond. All of these, based on carbon, silicon vacancy, germanium vacancy, tin vacancy, and most likely lead vacancy. We know it's there, but we're working on it. They all have the same property of effectively being better. Right, I'll just leave it at that. The optics is better. The spin is not better, but can be made better. And they are the right the group of color centers, quantum systems to focus on. I'll pass that. So this is just to show you an example of what the optical transition looks like. It's very sharp, atom-like, and it's a much more suitable system for quantum networks. And these are the 3 papers that I'll highlight, basically around that time, for silicon vacancy. Once we figured out that this is workable, these 3 papers became the roadmap for US in terms of building the US version of a quantum network, quantum internet. But instead of NV centers like Europe, they're using silicon vacancy centers, the first one on that column, as the choice. But it's again diamond. And it is based on structured waveguide structures to improve light coupling, so it's actual diamond-based device, but it's again the same concept of using color centers in diamond for quantum networks. But there's more fun at the bottom. We'd like to go further down, and we think of all these individual ones, tin vacancy center is even more superior. So there's a possibility that you can solve most of the problems that silicon has with tin. We'd like to invest into it, and that's what we're working on. I'll pass that now. So one of the things we have done is to demonstrate, we scale them, then we can actually look into not only just communication part of it, quantum networks, but distributed quantum computing elements, including the optical interface. But I'll come to the second part. The second part quickly is going to be on the sensors, and I find that quite exciting. These systems, if I consider a quantum object, we spend a lot of time trying to isolate it from the environment. So if you have a lot of noise in the environment, that's bad. But if the noise in the environment is interesting, that's not so bad. You actually use the fact that the environment affects the quantum object and see if there is a mechanism for it to operate as a sensor instead. So instead of isolating it, you actually introduce it to the environment and hope to learn something about it, if it's possible. So one area for that, given they work with spins, will be some sort of magnetic field. And the concept is, of course, magnetic resonance imaging, or NMR, nuclear magnetic resonance, electron or nuclear. And the concept is, can we actually do the same measurement, the same concept, using a single spin? Can we actually have a single spin NMR? Can we actually have a single spin sensitive NMR? These are difficult questions. So the way it works is, let me take that up. There we go. The way it works is that now we're looking closely into the way that red blob, the internal degrees of freedom of that red blob works. The MS0 and MS plus monostates are split by crystal field. Diamond forces the color center to have that nature, that property. But the MS plus and minus 1 states are degenerate, again, from quantum physics. So they have to remain degenerate. And we drive optically, and when we drive optically, something magical happens. What happens is that the system resets itself into MS0 state. So 95% of the time, it's polarized into the MS0 state. Okay? So if you do nothing but simply shine red light on it or green light on it, it sits at MS0 state. And if I apply a microwave and sweep the microwave field, this 3 gigahertz compares roughly to your microwaves at home. So if you sweep a microwave field in the vicinity of the color center, then what happens is that at some point you're resonant, and when you're resonant, you disturb this shelving. You disturb this resetting of the spin. When you disturb it, the MS plus minus 1 states get population. Luminescence from that state is weaker than the MS0 state. So simply by looking at number of photons the system emits per second, the rate, how bright it is, as a function of the microwave field, you trace out that pattern. So you get a little dip, you get a little signal when you're resonant. Now this is not really helpful, except when there is a magnetic field. If there is a magnetic field that splits, the MS0 and the MS plus and minus 1 states all split, and now I get a doublet, and the splitting of the doublet corresponds to the magnetic field it sees. So it measures magnetic field by the splitting it has between those two. Right? And it is a quick example of that signal. We're sweeping microwave, and the signal drops and it splits more. And the magnetic fields we need for this are Gauss level, so it's very small, quite minute magnetic fields. And if that magnetic field is generated by another spin, which is what we're hoping for NMR, we will be picking up that signal as well. So the concept of optically detected magnetic resonance, of course, goes back quite a lot, 1920s even, 30s rather, and the diamond comes into play around 1980s when we could see that we could do this shelving, this resetting of the spin, and then the actual first single NV experiments were started around 95, 96. So it's relatively recent, I would say, that it gets into single NV magnetometry and the ensemble. And it fits very nicely in this chart of sensor families that we have available to us today. This axis is detector target separation. That's how big of a volume you're integrating. That's what it says. All right. What's the size that the smallest size you can detect, and how far are you from that source? And the x-axis is how sensitive are you in detecting the magnetic field. The most sensitive things are not the NVs. We have force sensors. We have other things, microhole sensors. Squids are the best ones, but they're a bit more bulky. So you can see that the blue is more the NV center, the diamond sensors, and it fills a gap. What used to be a gap, it kind of fits there nicely, so it serves a purpose. And its main advantage is that it's very small. We can actually make the distances very small with diamond. And these diagonal lines are quite important. The first one is what it would take with the combination, what it would take to detect 1 million electron spins. If 1 million electron spins all worked together, like NMR, but in EPR, that's where you need to be to detect it. Next one is 1,000 electrons. Next one is 1 electron. And the last one is 1 nuclear spin. A single nuclear spin would produce enough signal for you to detect as long as you're in that area. And that's where NV actually touches, that level of sensitivity. So what can you do with this very quickly? You can have a diamond slab. It's very easy to have nice, clean surface diamonds. So instead of your very cheap optical, microscope slide, instead of a microscope slide of glass, maybe you take a microscope slide of diamond. And if you do that, or a very thin film covered on it, if you have your color center a few nanometers below the surface, 4 or 5 nanometers below the surface, then whatever you put on it, you will be able to pick up any magnetic signal from that object. So if you do that experiment, you have an integration volume, a small volume right above, and whatever is in that volume that has magnetic properties, spin, for example, like all atoms, it will produce some signal for the electron, for the quantum emitter to see. And what you're seeing here is quantum control as if it's a qubit. It's us doing quantum control as if it's a qubit, but suffering at various times with sharp peaks coming down when you hit a resonance that it has to do with the environment. The environment drives DNB as if you're applying the microwave. And it tells us effectively a fingerprint of what is out there. And here is one example of that. World's smallest NMR machine is 5 nanometer cube volume. It's from Stuttgart. 5 nanometer cube volume where they can tell difference between different species of hydrocarbons as hydrocarbons go around in this environment. So it's very interesting. And the final frontier is the last piece that I'll talk about is, yes, this is good to be able to put something on your very expensive cover slide, but can you go inside, the ultimate frontier, can you go inside the cell? Can you make measurements inside the cell? And does it even survive? And there is a way to do this. So instead of a large macro diamond piece, you can actually work with nano diamond. So diamond that is 20 nanometers, 30, 40 nanometers in diameter, very small, but containing these quantum objects. The interesting thing is these systems don't require cooling. They don't require special lab environments. They work under ambient conditions. Ambient meaning all the way from 4 Kelvin, very cold temperatures, to a couple hundred degrees above room temperature. So it's very robust. It works under very high pressure, and it works under high electric fields. So we designed a little chip, called it the cubic. The chip includes local temperature control, feedback, microwave control to be able to bring electrical control to be able to bring in all these controls. But what goes on it, on the chip, is either a microfluidic channel, so we can pass biological samples, or a little cuvette where cells can grow and eat nanodiamonds as food. And interestingly, nanodiamonds are very attractive. Cells don't mind them at all. Anything nano usually is toxic. Diamond isn't, or continues to be non-toxic. So cells eat them and don't mind them. So you can end up with cells with nanodiamonds inside, like this. Here's a live cell, and if you zoom in, you'll see red dots, red spots. Those are nanodiamonds that are glowing in their pinkish hue, and we can then do analysis to see exactly where they landed. And if they're not bound to anything, they can float about inside the crystal. And when they float about inside the crystal, we can make local measurements of magnetic field, ion concentration related to magnetic field. What I didn't tell you is that we can also do a similar measurement to understand temperature, and we can also trace out, just like this, we can actually trace out the nanodiamond as it wanders around inside a cell environment, reporting back continuously without disturbing the cell. And then we can map out its full trajectory over 40 minutes, because it doesn't bleach, it doesn't die out. It lives in the cell as long as the cell is alive. And it continues to explore the cell like nothing is happening and reports back local temperature and ion concentration. And there are parts where in this video you'll be able to see it does Brownian motion, it's a liquid environment, and occasionally it gets a big jump, gets a kick. This is where transport in cell is taking place, and things that are moving hit it, and then it flies off. So we can actually map out the transport channels. So there's a lot to do there. So there's simultaneous viscosity measurement extracted from the Brownian and non-Brownian part, as well as temperature dependence. So now we're learning about the physical properties of a live cell, not the biology part, but physical properties, and that might shed light onto some of the biological features that's going on. Again, using the same element that we used for quantum networks, basically the same principle. Finally, to wrap up, I hope I convinced you that the two far ends from each other, that two groups that would never normally talk to each other, we're bringing together through, again, diamond as a concept. To reflect on these optically active spins, these materials that carry these spins, even though I'm promoting a particular color center in diamond, we don't think we have the one that actually solves all our problems for quantum networks to sensors or anything else. We're not there yet. So there's a lot of work that needs to be done on material science side so we can achieve, we can combine that with quantum optics that we know to achieve this. The second is exploring alternatives, however, is a good and a bad idea. It's kind of weird. it's a good idea because we don't have the one, so we should go out and find the one. But also, if you can't just keep searching for nature to give you the one, you might need to build it. So not spending time on one long enough means that we're probably not going to progress it enough so it's operational. So we need to make sure the balance is right. And material maturity, even beyond the quantum object itself, it always takes time. So it's an effort to put it all together. I'll wrap it up now, and hopefully I convinced you that quantum optics, toolbox, and material discovery, material science can come together to give you opportunities to promote new technologies. And thank you very much. If there are any questions, I'll be more than happy to answer.
Now,
Urar Çeker. I have a couple of questions regarding, of course, the cell part. As a biologist, I am really excited as what can be some capabilities that you guys be doing mostly. So just wandering around within the cells, just randomly, that's good for physics most probably. But I would be interested more just, can you do any modification, or do you have any control all these nanoparticles so that you can just target them? I mean, it would be great that if we can go into the nucleus, do some just genetic modifications and stuff like that. So that's
Absolutely.
Really something, I mean.
That's a great question, and that's what we're working on right now. We are functionalizing the nanodiamond surface. It's quite amenable to functionalization. So if you're careful about it, so that you don't have graphite, you have a nice clean diamond surface, you can actually functionalize it quite well. And you can start targeting specific parts in the cell. We're trying to identify which parts are unique. Mitochondria is one, so we're trying to do that. And there are questions around the mitochondria when you bring external stimulus. When you cause oxidative stress, what happens to the cell? How does it react? How does each location, how does the inside of the membrane react? What happens to the ion concentration? To answer all those, we have to make sure that nanodiamond goes and sits somewhere. And that's the surface functionalization that comes in.
One more addition. So would you ever, would you be interested, or just did you ever try to grow this nanodiamonds within the cells, just not letting them eating the cells, just not feeding them from outside, but because there are all those vacuoles, and there is today just people can do acoustic-based genetic modification and stuff like that. So there's a lot of room, I think, to develop in that regard.
I would love to. I think our biggest challenge is diamond, as you know, forms under very extreme conditions. So even when we grow diamond in the lab, it is under still those very extreme conditions, high pressure and high temperature thousands. So that makes it difficult to synthesize. So it's not a chemistry that does it, it's the high pressure, high temperature part that limits us. Beyond that, I'm not sure. But what happens is when we feed the cells, we feed them also nanodiamonds, and they're happy. They take them. They don't coat them with cell membrane. They don't try to get rid of them, so they can stay. But if we functionalize it, then they can go and attach places. Those are the two ways we can operate. But growing inside is a challenge until we come up with a low temperature version.
Okay, sorry for my illiteracy. So
no, it's fine.
Thank you.
And nice to meet you, finally.
Thank you, Mete, for this excellent talk. So I'm Selim Hanay, as you know. So I have a question about the electric field sensing. Can we also use these nanodiamonds as a reporter for the local voltage levels? And do you have any plans for using them for excitable cells such as neurons? And
yes, exactly. So indeed, it does work that way as well. So basically, what I didn't mention, of course, I skipped over, is that you have these three-level scheme, right, under some finite magnetic field, which you might apply a few Gauss without disturbing anything. You have the MS0 plus minus 1. These two split by a magnetic field through Zeeman, but the center of these and MS0 state, they split by temperature or strain or electric field, all three. As long as you control the other two, the third one becomes your parameter that you're most susceptible to, and you can sense it. So electric field is one way where this can be done.
Excellent. Just a quick follow-up. And from what I see, you are not really, let's say, susceptible to intensity fluctuations because you are making frequency measurements as well. I think it's also giving a lot of robustness in your measurements, right?
That's right. I mean, if basically there are fluctuations, intensity fluctuations, we stabilize the laser to minimize those. And what we're looking for is effectively a differential measurement. So in those experiments, what I didn't show was how fast we can tell where the nanodiamond is inside a viscous environment. And the way we do this is we take the laser light, we stabilize it as much as we can, sure, but not much more than that. And then we dither it. Our laser isn't stable. It rotates around a circle, and we record intensity at each location on that circle. We sample it, and then we see if that is balanced or lopsided. If the ND center has moved to one side, nanodiamond has moved to one side, we'll get more photons on this arm than this arm. It's a very fast, and so it's a bit of inference. But then we know that it's moved, so we move with it. So that's how we actually keep tracking where the NV center is with low excitation. And then because we're looking at in this curve that you saw, we don't actually sweep microwave through every single time. We park on the four ends, and we do 1, 2, 3, 4, 4-point measurements to tell if that peak also moved or not. So we do the differential, essentially.
Excellent, thank you.
Thank you.
Thank you very much for the excellent talk. So I would like to ask, do you have a notion of what the one material that you mentioned to be? Any ideas?
Yes, it needs to operate under ambient conditions. It needs to be integratable into any device of my choice. It needs to interact with the environment and me strongly, and also not interact with the environment strongly. That is the problem.
But any candidates?
Any candidates? I think diamond will go a long way. I'm not sure it's the right one, of course, but for now it does offer promises, and we'd like to explore that. The main advantage is that it really is room temperature. I mean, just all the quantum properties, none of the quantum properties require cooling, effectively, and that's a big advantage. There is a competitor. We're also working on that, and that's hexagonal boron nitride. It also happens to show room temperature spins with optics related, and it has other properties. It's not as hard, which is a good thing. You can actually tailor it a bit better. It's layered material by nature, so there are other opportunities you can do. So we're exploring that at the same time. But as of now, I wouldn't say there's one material I would put money on. No, rather, I should put money on everything. So we do the research.
Present the plaque in memory of this event.
Sevgili Mete Hocam, bugünün bir hatırası olarak şöyle bir şeyimiz var.
Çok
Size
teşekkür
takdim
ederim.
etmek isterim.
Tabii ki.
Nasıl duralım? Şöyle duralım, şöyle ben vereyim.
Çok teşekkür ediyorum.
Tekrar.
Çok sağ olun. Çok teşekkür ederim. Çok teşekkür ederim.
We now have a reception. We're inviting you to the area. Thank you very much.
Thank you.